Ready? All right, thanks to everybody for coming. Wow, everybody got quiet before that was really weird.
You're holding that pointer.
Usually I have to like say something for people to cool. Yeah, that's right, scream that thing. All right, well, it's my pleasure to introduce today Juliet Pilewskie. That's how you pronounce it, yeah? Who's a master's student of mine, wanting to do a PhD here in the AOS department. Juliet joined my group almost 2 years ago now. I was trying to figure out how to phrase this. She is from a competitor school, let's say, of mine, and we had a speaker here from Colorado State University on Monday. It's probably fitting that we have a speaker who went to the other Colorado school. Let's leave it at that. No, she went to CU in Boulder, did a physics undergraduate degree, and I did joke a lot with her about the angst that I had about bringing on a CU buff into my group. But things have worked out. We don't fight too much about it anymore. We don't talk football, that's it. But anyway, so Juliet did a physics undergraduate degree, and I really like, so that's sort of near and dear to my heart as well, because I'm a physics undergrad and also a physics master's student. And I think for a lot of us in physics, it takes just sort of one event or moment in our life or one experience that makes us realize that we're excited about atmospheric science and want to kind of get into this applied physics field. And Juliet had that moment, apparently when she was taking a nonlinear dynamics course and got exposure to the Lorentz model and started to get interested in atmospheric science and weather. And then I guess you follow that up by doing an REU using satellite data sets, and so that's what sort of brought her to apply to AOS and come and join my group. Just as Juliet will obviously talk a lot about her research here, but Juliet has a fairly rich, let's say, other life. She's a very sort of artistic person, sings, plays piano, ukulele, is learning the guitar, and also has a background running triathlons in undergrad and is looking to get back into that here in Madison. So without any more ado here, I'll leave it to you, Juliet, to present your research.
Yes, well, thank you very much, Tristan, for introducing me, and thank you everyone for joining. So today I will be discussing the precipitation and radiative responses to convective organization in the tropical North Atlantic. So I'll just start with a brief outline of everything that I'll be discussing today. I'll start by motivating this talk by introducing the interactions between climate and deep convective morphology. So what exactly this convective organization, how it evolves over time is, as well as its significance and current limitations to observing it. And then I'll be looking at convective aggregation and idealized models as a physical example for convective organization. And then I'll go on to my guiding research questions, overview of data sets and methods that I'm using, results, observing relationships between convective attributes, my discussion, and future work. So to begin, convection is organized and can be organized across varying lengths and time scales. We begin by just looking at Bernard cells, which is an example of closed cells that typically form in large areas of subsidence, and this occurs during large cold outbreaks. And then we can look also at convective organization in terms of mesoscale convective systems. This is in the tropical North Atlantic. And then also convection can be organized in terms of tropical cyclones, shown here. So we can see, all of those were satellite images, and we know that they form, but we don't exactly know how they form and the, I suppose, length and spatial scales in which they form, and there are some difficulties in observing them. First of all, because they occur frequently over ocean, it's difficult to use ground-based observation systems. They occur across a range of length scales, and so it's difficult to parameterize convection in models, particularly climate models. It can be also difficult to partition cloud types such as anvil from the deep convective core, which I will go into a little bit later. So this has implications for inaccurately diagnosing radiative impacts. And so all of these are missing. So all of these are missing key features, like we're not able to observe some key features, so we need to determine the spatial scales, interactions with environment, and how they might change with warming in order to really understand the physical processes that are underlying these convective systems. So they have a large implication for influencing climate. This, first of all, is just a vertical cross-section of CloudSat reflectivities with height on y, latitude on x. And for convective systems, the height of the systems can be deduced to, we can observe the net radiation at the top of the atmosphere because these high clouds have implications for both increasing the shortwave reflectivity, increasing reflection of shortwave, but then also enhancing the absorption or weakening the outgoing long-wave radiation. So these effects essentially are currently canceling each other out. And then there's also the width of the anvils that influence exactly how much long-wave radiation can be observed. So the radiation emitted from the high cold clouds is different than from shallow clouds or clear sky, and that also changes depending on how much space the anvils take up. And so then the depth of these convective systems also impact how much reflectivity or how much shortwave radiation is being reflected. So combining all of these, we can start looking at how these convective systems influence high cloud feedbacks. So potential high cloud feedback that was proposed by Linson et al. In 2001 is the infrared iris hypothesis. Now, this controversial hypothesis introduced that with an initial climate warming due to increased CO2 concentrations, there was a reduced cloudy and moist area due to precipitation efficiency increasing in the convective core, which caused less detrainment to the anvils to occur. And so then this increased the outgoing long-wave radiative cooling, which then reduced warming, and so act as a way to modulate the enhanced warming. Now, I keep forgetting to use this. So using observations, we can begin looking at some of the characteristics of these storms and the processes driving them. With the infrared iris hypothesis, with the cool regions enhancing and the convective regions getting smaller, some scientists have put forth the idea that convective aggregation is a possible physical mechanism for this. And so this next slide, I will show a video, which doesn't show up very well in this, so I will have to go to So this is a cloud result. Ooh. Is there a way to slide or drag?
Drag it to one side probably, that you're not mirroring your monitors.
Oh, there we go.
Got it?
Okay, so this is a cloud resolving model in radiative convective equilibrium, meaning that the radiative cooling is balanced with convection, or heating from convection in the form of latent heating. And we see here that you can see this, the blue region, which is a region of low humidity, is increasing. And these regions with the convective clouds shaded in white and gray, as well as the red, which is high levels of humidity at the surface, relative humidity at the surface. This is expanding, and this is becoming smaller and being more confined in a smaller region. So let's just stop this.
What causes that organization?
So that's a good question, and I will go into that.
So that's probably column humidity in the colors, right?
Yes, it is column humidity. Yep, exactly. Okay. So, appreciate you guys' patience with that. So just to recap, convective aggregation is this randomly distributed convection which goes to organized convection despite homogeneous boundary conditions. And it becomes localized, or convection becomes localized to a single cluster. And the dry regions get drier and moist regions get moister. So what causes convective aggregation? There's been some studies, and this is all in terms of a idealized numerical simulation. So convective aggregation has been found to be sensitive to sea surface temperatures. And so at sea surface temperatures of what the Earth is currently exhibiting, around 300 Kelvin, enhanced pool or radiative enhanced regions of dry pools become apparent in dry regions, and we have a lot of strong outgoing long-wave radiation. Meanwhile, there's moist regions which have weak outgoing long-wave radiation, so this coupled feedback acts to increase these subsidence areas but also decrease the moist regions. And then also, a more indirect effect with this occurs when a shallow circulation is introduced in the dry regions, which further transports latent heating or moist static energy to these moister regions. So then, for sea surface temperatures larger than what we're currently experiencing at around 305 Kelvin, but then also contained less than 310 Kelvin, a surface enthalpy flux feedback, or these latent heating, or latent heating in these regions and moist regions, act to enhance the convection and these updrafts in the already convective regions. And this is because we have these strong surface winds in the moister regions, whereas we have weak surface winds, and there's not really there's not enough to enhance the outgoing or the latent heating in the weak and dry regions. So then, how can convective aggregation impact climate? So again, this is in terms of the numerical model with convective aggregation and sea surface temperatures changing, and each of these lines correspond to different sea surface temperature. We see that the cloud fraction changes. So this cloud fraction is due to these enhanced cool regions that are showing to decrease in the ample cloud. And we see that that's most apparent way up high in the tropopause for high sea surface temperatures. So then there's also a temperature change, and seeing that for really high sea surface temperatures, you're actually getting a warming of the upper troposphere. And then there's a relative humidity change for all of the sea surface temperatures that we're seeing there's a decrease. So again, these cold regions are drying. So Taking a step back and just trying to relate these numerical examples to more of satellite systems. Convective aggregation, is on a different time scale than a lot of these satellite, or than what we can expect in satellite observations. So this is just an image of, again, the CloudSat radar reflectivity profile. And we can see that we can track the characteristics of convection, because we can just tell that there is a change in the anvil traction, or the anvil cloud area, just from going back between these two. We also see that these convective cores, so each of these are convective cores, we can tell that those can aggregate into a pumped region. So I'll go on to my research questions. I would like to just first preface these by saying that now we're going to just look at how convective organization can be observed, and what are the physical processes underlying how convection is organized. So I'll begin by introducing, or just by mentioning convective intensity and area, and explaining what those different metrics are. So what are the relationships between convective intensity and area in different environmental regions? Then how does vertical intensity of convection impact precipitation production? And then is a shortwave or long-wave radiative response to the strength of convection dominant in a given region? And then how does the strength of convection depend on the environment? So for my data sets, I'm using co-located Earth orbiting and geostationary satellite observations. So the low Earth orbiting satellite observations are from the A-Train, which is a satellite constellation that all pass over the equator at roughly 1:30 p.m. local solar time. And this is really good for being able to use these co-located data sets, because they all go long track at roughly the same time. So I'm using measurements from CloudSat, Calypso, and Aqua. And then I'm also using PATMOS-x for the climate record that is here at SINS and SSEC, which supplies geostationary data, so that I can get more of a spatial and temporal aspect to these convective systems. And then the data sets are from 2007 to 2010. So just to give a nice visual of what all of these data sets look like together, here is a radar reflectivity profile with the reflectivities from the CloudSat W-band cloud profiling radar. Now these reflectivities will be used to diagnose the intensity, the vertical intensity of these convective systems. Now these points up here are what are called convective flags. They're from a CloudSat product, 2C precip column, which uses the radar's attenuated signal when it hits precipitation to diagnose where exactly precipitation is occurring. And so I'll be using that to for another metric. Next, I have, and this is all along CloudSat overpass. And then here are, here we go. Here are Amsuri rain rates, and Amsuri is on board Aqua. And notice how the rain rates are lining up very well with these convective cores, or convective regions. And then I also am looking at the environment, supplying some meteorological context. So vertical motion, or Omega 500, sea surface temperatures, and CAPE from the Meritu CloudSat co-located product. And then all of these values are averaged over the CloudSat path. And then finally, looking at cloud radiative effects, which I will describe in detail a little bit later on. Long wave in blue, short wave in green, and then net cloud radiative effects using a blend of observations from CloudSat, Calypso, and MODIS on board as well. And then finally, the spatial context is PATMOS-x cloud temperatures, which is, so we're using cloud retrieval on geostationary image, or imagery, and this is matched CloudSat's overpass, which is this green line here. And this whole box is about 15 by 20 degrees. So going on to my first question, what are the relationships between convective intensity and area in different regions? So just to describe, or just to, I guess, create a proxy for, or have a proxy for convection, we use vertical motion because convection is driving a lot of the vertical motion in the tropics. So this is a map in the tropical North Atlantic Ocean for where for data between 2007 to 2010 averaged for each 10 by 10 degree grid box. And it's an annual mean. And so we noticed that this region here is, or along the ITCZ band, or the ascending branch of the Hadley cell, we see negative values of Mera vertical motion corresponding to large-scale ascent. And then here we have positive values of Mera vertical motion corresponding to subsidence regions. So for the remainder of the talk, I will be focusing on two different regions, one of ascent A and then subsidence S. And these are the locations that I'm noticing most difference between each other. And then I'll also be looking at two different time periods of convective activity. So here's for March, April, and May, which is typically a less convectively active time period in the Northern Hemisphere, and then August, September, and October. So for characterizing vertical intensity of convection, what has typically been used is cloud top temperatures less than 195 Kelvin, because satellites are able to detect these really, really high, exceedingly cold clouds, and so they flag that as deep convective cores for cloud top temperatures of this. However, this is not a super direct measurement of like what's actually going on with the cloud microphysics. And so here's a new variable, which is considered the cloud's center of gravity, and it's adapted from Stora et al. In 2014. It is the height, it's a calculated height at which the mean weight of the cloud is located, and it's weighted by CloudSat's W band reflectivities. So it is, you can actually tell how high the largest hydrometeors are being wafted into the atmosphere. And I'm calculating this only for precipitating clouds. Here is the equation, with Z being the measured reflectivity at each level I. H is the height of each level I from the surface. So then, following the same method that we did for the Mera vertical motion, again, here's a map of the mean cloud center of gravity only over those precipitating regions. And we see that in the region of ascent, it corresponds to a higher cloud center of gravity than the region of subsidence. So this region is showing about 4 kilometers, that's where the cloud center of gravity is, and then this is showing for about 2 kilometers. And I want to say that this is roughly the mean cloud center of gravity over the CloudSat path, which is then, we add up all of those CloudSat overpasses within each 10 by 10 degree grid box, and then average that for all 4 years. So then looking at just a cumulative density plot, we see that the region has a larger impact than the season on convective intensity, meaning that for both the convective or the non-convective, less convective time periods, and more active convective time periods, we're still seeing that the cloud center of gravities are larger in the region of ascent than in the region of subsidence. So then characterizing the cold cloud area, we use a fraction of cloud top temperatures less than 235 Kelvin from the PATMOS-x data to matched to CloudSat. And then again, here's a map. And this is showing that in the region of ascent, we have a larger fraction of cloud top temperatures less than 235 Kelvin. Oh, and this includes both the icy anvils and the deep convective cores. Yes?
And for all this, when you say region of ascent, you mean the region that has mean for over 4 years has mean ascent?
Yeah.
Okay.
Yeah. Yes. Thanks for that clarifying that. Yeah. Mm-hmm. And then here in this region, we're seeing that there's a smaller fraction of cloud top temperatures less than 235 Kelvin, corresponding to a smaller area or cold cloud area. And this all makes sense given the environment because we expect for a larger vertical ascent that there are typically more clouds that are being generated as opposed to the subsidence regions. And then this also shows that there is more of a dependence on region as opposed to on season. So now, going back to the question of how does the cold cloud area vary with vertical intensity, here's a scatter plot, and it's quite a lot where we're seeing a large spread in values corresponding to the region of ascent. So I'll just focus on the region of subsidence during the high convective activity time period, which is shown in orange. We see that the linear regression shows a small sensitivity between the storm area increasing with intensity. So this is to physically understand this. When convection occurs in subsidence regions, that tends to stabilize the atmosphere, or subsidence corresponding to large downdrafts, tends to stabilize the atmosphere in these subsidence regions, so the convective clouds spread out. And then we're getting a larger cloud area. And so just to summarize, the storm area increases with convective intensity in subsidence regions during the active convective time period. And intense convection is found to exhibit a broader distribution of storm areas in regions of ascent. So then going on to my second question, how does the vertical intensity of convection impact precipitation production? So for characterizing precipitation, we are using conditional mean AMSURI rain rates, or calculating these mean rain rates along the CloudSat track only in regions that it is already raining, so as to not be averaging over 0 values. So we're seeing that, again, in the region of ascent, this corresponds to high precipitation rain rates of roughly 4.5 millimeters per hour. And then in the region of subsidence, this corresponds to smaller rain rates. And again, this is more of a regional dependence than seasonal. So, I forgot to mention this earlier, but each of these scatter points they correspond to every single CloudSat overpass within the 4-year time span for each of the given regions and seasons. So I forgot to make that clear in the last scatter plot, but I hope that was somewhat obvious. So in this plot, we're showing that precipitation increase is on the y-axis and vertical intensity is on the x. And again, I'm not going to go into the ascending or large-scale ascent regions very much, just because there is such a large spread in these data points. So looking at the region of subsidence, we see that there is some seemingly high correlation, although I haven't tested these statistics yet. Seemingly high correlation between precipitation increase with vertical intensity increase in these subsidence regions. So then, just to summarize again, rainfall increases with convective intensity in the subsidence regions. And this is seemingly physical. And then we again see that there's a large spread in how rainfall responds to convective intensity in regions of large-scale ascent. So then going on to my third question, is the shortwave or long-wave radiation response to the strength of convection dominant in a given region? So just to give a general background on cloud radiative effects, the shortwave cloud radiative effect is the difference in top of atmosphere radiances, so incoming minus outgoing for a cloudy region, minus the clear incoming minus outgoing, minus the radiances in a clear region. And so this value is typically negative for clouds, and that results in a cooling effect. And then for the long wave cloud radiative effect, it's similar to short wave, just with long wave now, and if it's positive, then it is a warming effect. So then, again, here's a map of the shortwave cloud radiative effects, and we see that the negative shortwave, or shortwave in the ascent region is more negative than it is in the descending or subsidence region, whereas in long wave cloud radiative effect, this value is also more negative. The long wave is also more negative in the region. Oh, sorry about that. This box is supposed to be here. It's more negative in the region of ascent, or more positive in the region of ascent than it is in the region of subsidence. Yeah, my bad. This box was supposed to be here. This one's supposed to be here.
Juliet?
Yes.
Just one question.
Yeah.
Is there any significance to the fact that box from between 0 and 10 latitude is over land?
So that's a really good question. Yeah, I mean, essentially, I at first just chose that region to look at just because it was showing the most vertical motion. But there are land effects that would be significantly changing all the characteristics that I'm looking at, I believe. And so in order to do a more in-depth investigation of this, I first should be looking at comparing ocean versus ocean, I think.
How many of the retrievals are different over land versus over ocean?
So they're roughly the same, yeah.
So the retrievals at least are the same?
The retrievals are the same, yeah. So they're roughly about the same amount of data points within each region. I was just kind of like, oh, that region is darkest and lightest, so looking at the most contrasting regions without really taking into all of the environmental impacts. Okay. So, yeah, but.
And we're able to, the land effect, stone effect, I know sometimes retrievals are a little bit different, like
yes.
The method for doing
yes.
a retrieval can be different over land versus over the ocean.
Yeah, that's correct, and especially for precipitation, it could impact land, it impacts how precipitation is being gathered and all that. Yes, yeah. So, to answer your question, yes, but I'm not exactly, that's a next step, which I'll have in my future work, so yeah, thanks. So then, combining these two cloud radiative effects into the net cloud radiative effect, which is just the summation between those two, we see that this whole region corresponds to negative cloud radiative effect, but it's more negative in the region of ascent than it is in, or region of ascent than it is in the subsidence region. And this is consistent with current findings of net cloud radiative effect in the tropics. So then to go on to how is the top of the atmosphere radiation varying with vertical intensity. Again, I'm looking at scatter plots, but I'm splitting up short wave and long wave and then going into net. We see that the y-axis, as short wave cloud radiative effect goes more negative, it becomes more dominant with vertical intensity. And so just looking at two different regions, but both in the convectively active time period, August, September, and October. This orange line corresponds to the subsidence region. We see that there is a strong change. So the short wave becomes really dominant as vertical intensity increases. Whereas this relationship isn't as great in the region of ascent. For long wave cloud radiative effects varying with vertical intensity, long wave is dominant in this direction, more positive, and we again see a strong difference, or a strong increase in long wave cloud radiative effects as vertical intensity increases for the subsidence regions in August, September, and October. But this is not as great in the region of ascent. But when you combine these, oh yeah, yes.
I'm just going to ask Juliet.
Yes.
It seems like in every one of the cases where you have a reasonably strong correlation, positive or negative,
Sure.
The points are clustered in the lowest couple of kilometers of your center of gravity of
Yes.
the cloud. So these are shallow clouds that have this impact, really,
Yes.
that determine that impact. Is that right?
Yes.
Okay.
Yeah.
Whether it's in the subsidence region or the ascent region.
Yeah, yeah. So that's one thing to note too, because I'm defining my cloud center of gravity based only on over precipitating regions. I'm not specifically distinguishing the deep convective cores from the anvil, from just shallow convection or stratiform precipitation just yet.
But the vertical
So-
intensity measure itself does that. If you were to look at just
Yes.
a bunch of orange points, for instance, you could find that most of the ones that you're sampling are really shallow.
They're
convective
really
clouds.
shallow, yeah.
Okay.
And that will become apparent more so in, I have some other plots of how convective intensity or the strength of, more so this, the strength, the vertical intensity varies with environment. You'll
Okay.
see that, yes,
Your center of gravity is defined only using the precipitating pixels?
yes. Do you have a comment about that? Okay. So then, when you combine the short wave and the long wave together, you see in fact that these near cancel each other out. And so we're left with almost zero increase in net cloud radiative effect or decrease with vertical intensity. And so then looking at how cloud radiative effects vary with cold cloud area, similar to the last couple of slides, only now on the y-axis is the cloud top temperature is less than 235 Kelvin. We see that for all regions and seasons, we're getting or short wave becomes dominant with, or becomes more intense as the convective, or the cloud area increases, and that makes sense because we're getting more short wave radiation being reflected. And so then for the long wave cloud radiative effects varying with cold cloud area, long wave is increasing as cold cloud area increases. Again, this makes sense because as the cloud area increases, it is able to absorb the outgoing long wave radiation and also also emit at a lower brightness temperature than the ground does. Effectively, that is a warming effect. And so then combined, we see that the long wave in this case dominates. So there is an increase in the net cloud radiative effect with the cold cloud area. And so this is a warming effect. And so just to summarize again, for both regions of large-scale ascent and subsidence, the net radiative impact of convection is invariant during the more convective time period, which is what we saw. And then the long wave radiative response is dominant for all regions as cold cloud area increases. And so then finally, how does the strength of convection depend on the environment? And I'll be characterizing the environment in terms of two different variables. First is sea surface temperatures. And this is just the distribution. It's a contour. These are contour plots of the distribution of vertical intensity on the y-axis versus sea surface temperatures along the x. And we see that in the region of subsidence, there's low vertical intensity corresponding to a small distribution in sea surface temperatures. So yeah, the highest the cloud center of gravity appears to be getting is roughly 3 or 4 kilometers in the subsidence regions. And then in the regions of large-scale ascent, this is interesting because we're seeing a bimodal behavior between convective intensity and sea surface temperature. I'm not exactly sure what to make of this just yet. But we're seeing that there are two different regions of sea surface temperature that's being that are prevalent with these different convective systems.
Did I miss? Are we looking only over the ocean now?
No. So
you said sea surface temperature.
Yeah. So then yeah, you're right. So it would be just in general surface temperatures.
Okay.
Not sea surface temperature. Thank you.
Okay.
Are they the same latitude,
Yes.
Del?
No.
Polar and the North Thames?
So, oh yeah, or these between
That's
these,
not the,
or
those temperature differences are not difference to latitude.
no.
Okay.
No. Yeah. So perhaps this bimodal effect could be due to, well, I'm not going to say what it could be because I'm not positive just yet. And so then looking at
Just shallow clouds versus deep clouds?
yeah.
Just that there seems to be a bimodal distribution of cloud depths?
Sure.
Well, is there more to it than that, or?
Yeah, but
It's not
here,
the
these-
cloud depths that are bimodal. Yeah,
It's
I'm wrong.
not the cloud depths, it's a
It's the
surface
surface
temperatures,
temperature.
but
Yeah.
you're still exhibiting the same cloud, or the vertical intensity. So maybe this is more just saying that you still get roughly the same vertical intensity with varying sea surface, or varying surface temperatures, no matter where they are.
So two
Still
different
roughly
kind
the
of
same.
modes of convection.
Yes.
Maybe forced in different ways. Maybe one of them is forced by surface temperature, whereas one of them is forced in some other way.
Yeah, that could be a reasonable thing to.
Or is it coincidental?
Like maybe SST gradients? My favorite mechanism.
Yeah.
Or is it coincidental that 300K in northern South America is approximately the sea surface temperature required for tropical cyclones?
Yeah. Yeah, so these are all really good things to consider. I would like to do so in the future. So then just looking at vertical intensity varying with Cape, or perhaps the potential for convection to occur, we see that these values of Cape are really small, corresponding to very small values of vertical intensity. That's maybe somewhat of an obvious conclusion, but yeah, it makes sense. And then larger values of Cape and a more distribution corresponding to the regions of ascent.
What about the slope?
Yeah, slope,
Yeah, in the spring there's a slope, and in the midst of the summer there's none. That's interesting. I don't know.
Yeah.
It just catches my eye. I wonder what's going on there.
Yeah, so I at first plotted this as a scatter plot and tried to do linear regression, and it was even more of a mess than my other scatter plots that I showed. So that's why I decided to display it like this. But yeah, no, that'd be interesting to look at. Yeah, see what this slope is. Yeah. So then, how does the strength of convection depend on the environment? Again, the region of subsidence connected to cooler SSTs and smaller cape than in regions of large-scale ascent. And then there's a large spread in surface temperature in cape with intensity in regions of large-scale ascent. So, just to conclude, again, here are all my questions. Looking at convective intensity and how that varies with area in different regions. We have an increase in storm area with convective intensity in the subsidence regions. How does the vertical intensity of convection impact precipitation production? See that precipitation increases with convective intensity in subsidence regions. And then, is the shortwave or longwave radiation response to the strength of convection dominant in a given region? We have that there are net zero radiative impacts for both regions during the active convective time period. And then, how does the strength of convection depend on the environment? We have cool surface temperatures and low cape corresponding to the convective intensity in the subsidence regions. And the reason why I pretty much just pinpointed everything that was going on in the subsidence regions, because I noticed that, so my main takeaway is just saying that there appears to be evidence for convective or for subsidence regions to be more sensitive than regions of large-scale ascent to convection. But there's still no significant net radiative responses to convective intensity. And so, I mean, this just brings up a really interesting feature. And there's not been a lot of work being done in actually looking at what updrafts do in subsidence region, or, well, what the sensitivities between these are in the subsidence regions.
Can you tie that to the Linsen hypothesis? Is that what you're trying to say here? Or?
Not, yeah, so.
You can keep going if you don't.
I mean, no, I thought a lot about how to tie this back to what Linsen is proposing. I feel like I don't have enough to gather, to provide some physical understanding to Linsen's. I just feel like I'm not quite there yet, but this is just a point
you
for
did show
further
the components, shortwave and longwave.
Yes.
And you're talking about net here, right? So
Yes.
I think you had actually said that it was a cancellation of the shortwave and longwave.
Yeah.
And I think Linsen only deals with one of the components is the
Yes.
problem. I mean, it's...
Well, but I guess broader, you have kind of what Linsen initially said in 2001 and the sort of broader idea that there's some effective
Right.
clouds.
I know like Sandrine Boney's working on this a little bit as well, and she's shown in other ways that the long wave and short wave offset one another. So yes, there is an effect, but like in terms of the dynamics and thermodynamics, but I think you actually did cover it in your talk, that if you isolate and just look at the long wave, which is what a lot of people want to look at for high cloud feedbacks, but you ignore the short wave, then you find something. But the area effect is actually sort of on the shortwave offsets the long wave.
Okay.
I think that's
Yeah,
basically, this is just purely from radiation,
yeah.
not dynamics or thermodynamics, but that's I think what happens in
Sure.
radiation fields.
Yeah. It actually depends on whether the vertical motion profiles are top heavy or bottom heavy, that offset.
Yeah.
How much of that offset happens?
Right,
It
and
has
I
to do
think
with the
that's, is
depth
that why
of
we're
the
seeing,
convection.
maybe this is why we're seeing it in substance regions. I was actually kind of wondering about your take on this, or if there's a reason that you think that we might be able to see that better, more clearly in these regions. But maybe we can talk more on
Yeah, sure. It's a really interesting data set, so keep
thank
going.
you. Yeah.
Why didn't you compute center of gravity for like all of the cloud instead of just the rain portion? Because wouldn't those change?
Yeah.
Wouldn't that capture the anvil more than just the convective cores if you did it for the entire cloud?
So I didn't want to take into account the anvils for the vertical intensity because that was being captured from the PATMOS geostationary. So the cold cloud area, cloud temperature is less than 235 Kelvin. So I was describing the cloud center of gravity specifically just for understanding the intensity of these updrafts, or yeah. Does that answer your question? Yeah. Okay. So then, just for future work, I would like to actually test my statistics. So how these relationships are observed in ocean-only regions as compared to ocean and land, which is what I did here. And that would kind of give more of maybe a control. And then filter out multi-layer clouds when calculating cold cloud area, because that perhaps could have skewed some of my results by enhancing the vertical intensity in some regions. And then explore how convection is influenced by other environmental variables such as total precipitable water to gather data on moisture as well as vertical shear. And partition between thick and thin anvils to more accurately diagnose radiative responses. Observe how these relationships evolve over the convective life cycle and changing environment, which I will be doing with PATMOS geostationary data. This is a 16-hour evolution of a convective complex. The middle one corresponds to a CloudSat overpass, but we can actually see how these are evolving with the PATMOS data. Each image here is 2 hours in between each other. And then so then look into how the distribution of radiative heating at the top of the atmosphere responds to convection. And then finally extend to the southern hemisphere and regions outside of the tropics. So then I would like to acknowledge some people. Of course, Tristan, I'd like to thank you for all of the time and effort that you have put into helping me motivate my project, and then also Larissa and Stephanie for being readers for my thesis, and then all the other faculty at AOS, just in conversations and classes that I've had from you, and Chelsea, Sue, Dee, Sonia, and all other administrative people, Create Group and all AOS Guide students, Sims and SSCC, Pete, I don't think I even said Pete, sorry. And then last but certainly not least, thank you to my family and friends that have continuously supported me. And that's it, thanks. Yes.
It's really interesting, Juliet.
Thank
Juliet.
you.
Two things came to mind.
Yes.
Early in your talk, when you're talking about drying and warming,
Yeah.
I'm interested in knowing what happens to theta E at about 100 to 200 millibars. Is there any change in the theta E, or is the cooling and the drying even out so the theta E stays the same as you increase the sea surface temperature in these simulations? So that's one.
Theta E goes up.
It goes up
Yeah.
as much as the sea surface temperature, or only a fraction?
Not as much because there's drying.
Yeah, okay, so
The
it's
overall
mixing up.
temperature still goes up with sea surface
Okay,
temperature.
okay. So that's cool. So that changes the outflow layer, most likely. Or is that a manifestation of a change in the outflow layer, aggregately of the convection?
Manifestation. So to first order the atmosphere is to a moist adiabat.
Yeah, okay.
And what moist adiabat that is
Depends on your sea
changes with
surface temperature. Okay,
Yeah.
okay. So I guess it's kind of related. And then the second is the subsidence region here, I think, spans 20 to 30 degrees north right off the west coast of Africa, right?
Yeah.
So that's got a parade of synoptic events with the
Yeah.
African easterly jet. So
Yeah.
some of those really blow up, I imagine, and some of them are just kind of mundane. And so is that maybe why you have a clustering, let's say 2 out of every 3 events is a mundane, shallow convective event, and then maybe every 3rd or 4th one is a blow up? And that might be why you get a preponderance of these low cloud events. they're happening frequently, but not with the same intensity. That would be one thing to
Okay.
maybe consider, I
Okay.
suppose.
Yeah. I'm just writing that down.
But have you looked at any particular segments in time of some of the things that are occurring in that particular box and noting if there's any synaptic activity of varying intensity?
I have not.
Okay.
That's good to look into. Yeah, particularly pinpointing some case events.
Yeah,
just
right.
looking at the,
Seeing what they
yeah.
look like. Because it's
Yeah.
interesting that the sensitivity is so strong there. It makes sense after what you've shown, but it would be
Yeah.
cool to be able to ascribe it to an almost mid-latitude synaptic process for once.
Sure.
You know?
Well, it's
So-
kind of like the easterlies,
Yeah, that's right.
being relatively quiescent for deep convective systems most of the time. Trade winds.
Yeah, yeah. It's kind of interesting.
The radar data set, could that be used to look at more, is that, I'm trying to figure out the sensitivity, like
Yes.
what kind of range of intensities are we talking about in terms of, like, I guess, rain rates?
Yeah.
I'm just
So-
curious, you can get to me afterwards too. It's
Okay.
fine, but I'm just trying to get a sense of, there's really interesting land-ocean differences in some things in terms of convective intensity.
Okay.
And so I'm just trying to get a sense of whether this data set could be used for that. That's what I'm curious about.
Can you go back to the scatter plot? Would that help, the scatter plot of rain versus rain rate and intensity, I think?
Yeah.
I think you can see the range on that plot. Only rain rate on the y-axis.
Yeah.
There, so that gives
Yeah,
you.
so.
Oh, but these are averaged over.
Yeah, they're
segments.
averaged.
Yeah, you want to know that it's, yeah, okay.
The individual, yeah,
But
these
maybe
are
the
average.
maximum, if you plotted the maximum rain rate on the y-axis instead of the average, that's some sort of an average.
Oh,
over
yeah,
the-
yeah, these are the averages over the, regions where it's only raining along the CloudSat overpass, yeah. So, since, I'm not exactly sure that since it is averaged, then maybe some of those special features are kind of canceled out, but that'd be good to, yeah, look into
It's just
them
curious.
individually. Sure. Yes.
So it's just thinking about global warming,
Uh-huh.
now you have more moisture, higher temperatures, more moisture, probably more clouds. Is this correct? Tell me if I'm right or wrong, just for take home message. It looked like when you showed the net of the net radiation, that it was pretty uniformly cooling, no matter if it's in the deepest tropics or in the subtropics, or you do have convection. There's some vertical development, it has a net local cooling effect. Is that fair to say or not? That your overall results are, yeah, -20 all the way across. Is
Yeah.
that-
Oh,
does that
yeah, sorry.
give some hope for global warming, that if we have more deep convection, it'll be top.
Yeah, so these were just correlation values. I didn't even mention that. But yeah, these were the slopes. So we're seeing that the change in cloud radiative effect per, I guess, increase in vertical intensity, or like if you were to, or to consider in this case, cold cloud area. That's
Is it too
That-
complex to really say such a simple thing?
I feel like that's too complex right at the moment. I think that, I mean, yeah. But that's definitely something that crossed my mind when just initially looking at this too. Especially, I mean, I canceled this part out, or highlighted it out just because I wanted to focus on these two regions. And also because I wasn't positive what this negative correlation was due to. But when I first saw it, I just was like, oh, okay, as storm intensity increases, and for some reason we're getting that the cloud radiative effects decrease. So that could have been,
So more important work needs to be done.
yes. Any other questions? Yes.
This variable COG,
Yes.
is that commonly used in studies like this for
It
convective systems?
So it just started being used. It was first proposed back in 2009 by calculating the mean cloud weight weighted by precipitation. But then this Storer paper, well, I'll just, this one other one in 2014 was the first one to use actual CloudSat reflectivity. So it's still a pretty new variable that has been calculated.
What's that variable, reflectivity?
It's using the reflectivities from radar.
Oh,
So
the radar signal.
The radar signal, yeah.
Now,
Yeah.
is the radar signal linearly related to precip density?
No, but it's related to the size of the cloud.
But I don't think it's a linear relationship, so I could have just thought it was kind of odd not to use a direct measure of the precipitation elements
Yeah.
as the weighting function. Maybe we could talk
Yeah,
later.
Sure, yeah, yes.
So I don't know as much about the geometry in the Atlantic, but I know
Okay.
in the Pacific, the shortwave and longwave cancel to first order, but there's variations by about 30 watts per meter squared geographically, even for similar rain rates in the cancellation. And it seems like you can tie that pretty well to kind of the overall vertical motion profile shape, and
Okay.
whether in bottom heavy cases your clouds are lower, so the long wave trapping effect is less, whereas in top heavy regions the long wave trapping effect is stronger. And so you can just correlate cloud radiative effect quite well with measures of top heaviness, and there's a strong correlation. There's a paper by Chris Brotherton in 2009 or 2008 about this, and Dennis Hartman.
Oh, okay.
So that would be an interesting thing to shift, and I know Dennis has had some students work on this as well. I know that it would be interesting to shift from just taking the omega at 500 hectopascals to also looking at the second EOF in vertical motion.
Okay.
And that would be a result that you would be really well set up to quantify in a way that Chris and Dennis were not 10 years ago when the paper was written.
Okay. Thank you.
Yeah.
It's really good. Look into that.
All right, let's thank Juliet one more time.